Module 21.3 concerns what is called an electric dipole. Dipoles are incredibly important, and as their name implies, di meaning two, poles. These are two paired but equal charges but opposite in sign. So if we had a plus 5 coulombs here and a minus 5 coulombs here, this would constitute what is called a dipole. Now, dipoles are very important. You'll notice they are electrically neutral, but the center of the positive electricity and the negative electricity are in two different places. In fact, water molecules are of this type, since if we look at the water molecule, we have the oxygen here and the hydrogen for H2O, and the hydrogens do not line up across the oxygen molecule, and this result gives us a dipole or center for positive and negative electricity, which is not exactly the same. Therefore, the center of positive electricity is in one place and negative in another, and we say that they're separated in general by a distance d. Then what we do is we define this as a vector, and we define this vector as p. That's a small p. Remember, p is also used for momentum, so you have to be careful. Q times d, where q is the positive charge, that's equal to q times the distance d. And the vector points from the negative to the positive. Negative to the positive. That's a vector here, and that defines the vector going in this direction for this dipole. Dipoles always have a direction. So in this particular case, if we had 5 coulombs and a minus 5 coulombs separated by a distance of 4 meters, then the dipole would be what? The dipole P for that system would be 5, the positive charge only, times the 4 meters, or 20. Well, 20 what? 20 of coulombs times meters. 20 coulomb meters. And there's no name for that also. And so the electric dipole is a vector that points from along the distance between the charges from the negative to the positive center. And many of these molecules are dipolar in nature, as water I just described. And this is kind of similar to the magnetic dipole. We're going to be talking about magnetic dipoles very extensively, because magnetism does not have a monopole charge. There is no such thing as a north pole or a south pole separately, but only when they're paired together in equal and opposite pairs. And so we'll therefore see why the magnetic dipole is of critical importance. But the electric dipole is of so much importance because you don't actually have to make an object charged. You just have to separate the positive and the negative charges by a little bit. And this happens with many molecules, and it affects the chemistry greatly. These also feel a force and a torque in an electric field, which we're going to talk about in the next section, 21.4.